Hi, in this video, we want to take a look at hypothesis testing with one sample. All right, this is we're going to be running through the PowerPoint slides from Essential Biostatistics by Bernard Rosner. It's a Cengage textbook. All right, so our introduction. Hypothesis testing framework specifies two hypotheses, null and alternative hypothesis. Hypothesis testing provides an objective framework for making decisions using probability methods rather than relying on subjective impressions. It provides a uniform decision-making criterion that is consistent. In a one-sample problem, hypotheses are specified about a single distribution. In a two-sample problem, two different distributions are compared. In hypothesis testing, what we're trying to do, we're trying to set up a decision, one or the other type of decision, two possibilities. And in hypothesis testing, we want to have a complete, full understanding of what's going on when we make a decision. Now, that sounds like a very trivial statement, but what we're doing is we're getting a full, complete understanding of what happens when we make a mistake, right? If I make a decision and I've got two possibilities, it's possible I made a mistake. I could have made, I should have picked the other one when I picked the one I did. Hypothesis testing is all about understanding completely, totally, and utterly what you're doing when you make a decision. And we're using probability and statistics to provide that full, deep understanding. All right, so we're going to have two hypotheses. We're going to call one of them the null and the other one the alternative. All right, the null hypothesis, denoted by H sub O, is a hypothesis that is to be tested. And the alternative hypothesis, denoted by H sub 1, is a hypothesis that in some sense contradicts the null hypothesis. All right, so we have two possibilities. We have one possibility is that mu is less or equal to some particular fixed value, or the other one is that mu is strictly less than a particular fixed value. So here, this represents the possibility that the true population average is greater than or equal to a fixed given number. The sub-zero is that fixed given number. And here is the alternative, that the parameter is strictly less than that hypothesized value. We have two possibilities. Either this is correct or this is correct. Suppose the only possible decisions that we could make are either that H0 is true or H1 is true. For ease of notation, all outcomes in hypothesis testing situations are generally referred to the null hypothesis. If we decide that H0 is true, then we say we accept H0. If we decide that H1 is true, we say that we reject H0. So there's four possible outcomes altogether. All right, so in statistics, we have some funny wording on this. We're either going to say that we fail to reject the null hypothesis or we reject the null hypothesis, one of the two. As we get through this, I'll explain why that is. All right, so now if I accept the null hypothesis, when the null hypothesis is the truth, is the correct conclusion, then I made the right choice. If I reject the null hypothesis when the alternative was correct, I made the right choice. If I accept the null hypothesis when the alternative was correct, then I made a mistake. So here, this is a mistake. There's a problem. If I reject the null hypothesis when the null was in fact correct, once again, I made a mistake. So two of the possibilities, one's on this diagonal, are correct, and these two off-diagonal entries are incorrect conclusions. All right, so what we're going to do is we're going to consider how likely am I to make a mistake? And we're going to use probability, statistics, and assumptions to do that. Now, furthermore, we're going to consider like the ramifications of an error. And so I'm going to consider how big of a deal would it be to make one of those two types of mistakes. One of them is going to be worse than the other. And I'm going to set things up so that rejecting the null hypothesis when it was the correct choice is worse than the other alternative. So what we want to do when I'm deciding which hypothesis is the alternative and which is the null, I'm going to set it up so that rejecting the null hypothesis, when in fact it is correct, is the worst outcome than this. So these two events, these two possibilities, I've made a mistake. One of them is going to have a worse ramification than the other. So in that, what I want to do, I want to set it up so that my null and alternative corresponds to this one being the worst penalty for a mistake, and this one's the lesser one. Then what we're going to do, we're going to consider how much of a risk am I willing to take to make this mistake. And to a large extent, in most situations, we'll actually ignore this one, the risk of this one in most situations. All right, so a type 1 error is the error that we're really trying to avoid. This is the probability of rejecting the null hypothesis when it is in fact correct, is denoted by alpha and is commonly referred to as the significance level of the test. The probability of a type 2 error, in this situation, the alternative was correct, but we went with the null. So notice that both of these, type 1 error, type 2 error, I've made a mistake. Why do we care about this? Because understanding these types of errors is important for us to fully understand what we're doing when we're trying to build up an objective framework, a complete understood framework of making a decision. This probability is a function of the parameter as well as other factors. It's usually denoted by beta. In general, we have control over alpha, and we have little, if any, control over beta. A lot of times we actually just ignore the beta. The power of a test is defined by 1 minus beta, which is equal to the 1 minus the probability of a type 2 error, which is equal to the probability of rejecting the null hypothesis, given that the alternative is correct. The aim in hypothesis testing is to use statistical tests to make alpha and beta as small as possible, which means rejecting and accepting null hypotheses less often. All right, so one sample test for the mean of a normal distribution, one-side alternatives. All right, so here, what we're going to do, I want to check to see my hypothesis is that the mu, the population average, is greater than a particular value or less than a particular value. The acceptance region is the range of values of x for which the null hypothesis is accepted or failed to reject. The rejection region is the range of values of x for which the null hypothesis is rejected. And since we've got two possibilities, we're going to be in one of these two regions with our data. If x bar is sufficiently smaller than mu sub 0, so this is the hypothesized value, then h naught is rejected. Otherwise, h naught is accepted. So this is for greater than. If h naught is true, the most likely values of x bar cluster around the hypothesized value. If the alternative is true, the most likely values of x bar cluster around the alternative value. Such a test based on sample mean has the highest power among all tests with a given type 1 error of alpha. A one-tailed test is a test in which the values of the parameter being studied, in this case, population average, under the alternative hypothesis are allowed to be either greater than or less than the values of the parameter under the null hypothesis, but not both. All right, so let's talk about a one sample t-test for the mean of a normal distribution with unknown variance. So here we're saying the alternative mean is less than the null mean. We want to test the hypothesis that, so let's look at the alternative first. So here our alternative is that the unknown population average is strictly less than a particular hypothesized value. And then the null hypothesis is that the true population average is greater than or equal to some the hypothesized value. Now, when sigma is unknown and I have a normal distribution, instead of normal, I'm going to use the t distribution. And here is my t test statistic. All right, so here, if I notice that my t is substantially less than a cutoff value, then we will reject the null hypothesis. If t is greater than or equal to that cutoff value, then we will fail to reject the null hypothesis. And here the author says we accept. A lot of other people say fail to reject the null. The value of t is called the test statistic because the test procedure is based on that statistic. This t is what's coming from our data after I do my calculations, and this is the value that I'm using to say, is it less than or greater than the cutoff value? The value of this t sub n minus 1 alpha is called the critical value because that sets the cutoff for deciding what we're going to conclude. And it all comes down to where is our data's calculated value, t, where is that in relation to that cutoff? And so here in this scenario, if t is less than the cutoff, we reject the null. If t is greater than or equal to the cutoff, we fail to reject the null hypothesis. The general approach in which we compute a test statistic and determine the outcome of a test by comparing the test statistic with a critical value determined by the type 1 error is called the critical value method of hypothesis testing. The p-value for any hypothesis test is the alpha level at which we would be indifferent between accepting or rejecting the null hypothesis, given the sample data at hand. All right, so the p-value is when I slap down the test statistic and I look at the shaded region farther out, that is my p-value. And that's after I have data in hand. That is, the p-value is the alpha level at which the given value of the test statistic is on the borderline between acceptance and rejection regions. Now, solving for p as a function of t, we get that the probability that t sub n minus 1 less than or equal to our test statistic is equal to our p-value. The p-value can also be thought of as the probability of obtaining a test statistic as extreme as or more extreme than the actual test statistic obtained, given that the null hypothesis is true. The p-value indicates exactly how significant the results are without performing repeated significance tests at different alpha levels. Guidance for judging the significance of a p-value. If it's between 0.01 and 0.05, then the results are significant. If the results are between 0.001 and 0.01, the results are highly significant. If it's strictly less than 0.001, then the results are very highly significant. If the p-value is greater than 0.05, then the results are not considered statistically significant. And if it's greater than 0.05, less than 0.1, then a trend towards statistical significance is sometimes noted. So if we have like strong belief from like subject matter experts information that it should be going this way, and we get a p-value between 0.05 and 0.1, it's technically not statistically significant, but it's, it's still like leaning in that direction, but not strong enough to make that conclusion. Determination of statistical significance for results from hypothesis tests. Either of the following methods can be used to establish whether results from hypothesis tests are statistically significant. 1. The test statistic T can be computed and compared with the critical value at the alpha significant levels of 0.05 with mu greater than or equal to the hypothesized value versus the alternative of mu strictly less than the hypothesized value is being tested, and T is strictly less than that cutoff. Then, in this situation, H naught is rejected and the results are declared statistically significant as long as our p-value is less than 0.05. Otherwise, for all the other ways of wording this, all the other ways, H naught is accepted and the results are declared not statistically significant. This approach is called the critical value method. Now, method 2, the exact p-value can be computed, and if the p-value is less than 0.05, then the null is rejected and the results are declared statistically significant. Otherwise, the p-value is greater than 0.05, and then H naught is accepted and the results are declared not statistically significant. This approach is called the p-value method. All right, now the one sample t-test for the mean of a normal distribution with unknown variance. So the alternative mean is greater than the null mean. All right, so what we're going to be testing, we want to test, is the true population average greater than some hypothesized value? And here are the null hypothesis is that the population expected value is less than or equal to the hypothesized value. With a significant level of alpha, the best test is based on T, where T is x bar minus the hypothesized value divided by n divided by square root, s divided by square root n. If T is greater than the cutoff, then the null hypothesis is rejected. If T is less than or equal to the cutoff, then we fail to reject the null hypothesis. The p-value for this test is given by the probability that T is less than T n minus 1, like that. All right, now one sample test for the mean of a normal distribution, two-sided alternatives. Previously, we talked about the expected value is greater than the hypothesized value, or it's less than the hypothesized value. Now we want to look at the possibility of equal versus not equal. The two-tailed test is a test in which the values of the parameter being studied under the alternative hypothesis are allowed to be either greater than or less than the value of the parameter under the null hypothesis. So here we're interested in either it's equal or it's not equal to the value. A reasonable decision rule to test for alternatives on either side of null mean is to reject the null if it is either too small or too large. So if it's too far to the left or too far to the right of the hypothesized value, we will reject the null hypothesis. Another way of stating the rule is that the null hypothesis will be rejected if T is either much less than or much greater than some critical cutoff values. And we will fail to reject the null hypothesis if T is between those two cutoffs. So the probability of rejecting the null hypothesis, given that the null is true, so here we've made a mistake, is equal to the probability of having T being too far to the left or too far to the right, given that the null is correct. You break up these two into two possibilities, and this is going to be equal to alpha. So typically what we're going to do, since we have this summation, we're going to set up our cutoff values, C1, C2, such that both of these probabilities are equal to alpha over 2. Now, the one sample t-test for the mean of a normal distribution with unknown variance, this is two-sided alternative. So to test the hypothesis that mu is equal to the hypothesized value versus mu not equal to the hypothesis value with a significance level of alpha, the best test, once again, is the t-distribution. All right, so if we see that we get a large t in magnitude, absolute value is greater than a cutoff, then we're going to reject the null hypothesis. If this should be less than or equal to here, this should be less than or equal to, then the null hypothesis, we fail to reject the null hypothesis and we tentatively accept it. So if my test statistic is far to the left, far to the right, we reject the null in favor of the alternative. If my test statistic is in the middle here, inside the cutoff values, then what we're going to do is we will fail to reject the null hypothesis. All right, so now the p-value for the one sample t-test for the mean of a normal distribution, two-sided test. All right, so here, the p-value is the probability under the null hypothesis of obtaining a test statistic as extreme or more extreme than the observed test statistic, where, because of the two-sided alternative is being used, extremeness is measured in absolute values of the test statistic. So when I do the alternative hypothesis of does not equal, equal sign with a slash, does not equal, I've got two sides to worry about. When I get my t test statistic, that's that fraction we looked at earlier, I slap it down, I look at the shaded region to the left, or if it's over here, I take it to the right. And then for my p-value, I double it because to take into account the possibility of being extremely left or extremely right. When is a one-sided test more appropriate than a two-sided test? Generally, the sample mean falls in the expected direction from mu, and it is easier to reject the null hypothesis using a one-sided test than using a two-sided test. A two-sided test can be more conservative because it's not necessary to guess the appropriate side of the null hypothesis for the alternative hypothesis. In some cases, only alternatives on one side of the null mean are of interest or possible. And a one-sided test is better than a two-sided test because it has more power, since it's easier to reject the null based on a finite sample if the alternative is actually true. The decision whether to use a one-sided or two-sided test must be made before the data analysis, before the data is collected, begins, so as not to bias conclusion based on results of hypothesis testing. Do not change from a two-sided test to a one-sided test after looking at the data. All right, because of that doubling of the p-value, you could be, if you notice that, oh, my p-value is 0.07 from a two-sided test. Well, if I was to do a one-sided test, that would be statistically significant, but two-sided is not. So someone who's unscrupulous could look at the data and then go, hey, I'm converting over to a one-sided test to get the results I want. Don't do it. Don't do it. One sample z-test for the mean of a normal distribution with known variance, two-sided alternative. All right, so the difference here is that instead of having an s in this fraction, I am using sigma because it's known. I'm going to call this z. And when I do my calculations on the distribution, I'm using the normal distribution instead of the t-distribution. That's the big difference. Everything else plays out the same way, just that we're using the null distribution, the normal distribution, which is represented here. Now, a one sample z-test for the mean of a normal distribution with known variance, one-sided alternative. All right, so here we have mu1 and mu2. Mu1 is strictly less than mu2. To test the hypothesis that mu is strictly less than mu0, and with a null of mu greater than or equal to mu 0, with a significance of alpha, where the underlying standard deviation is known. This is important. The best test is based off of, it's basically the same fraction, but instead of S, I have a sigma. If Z is less than our cutoff, then we will reject the null hypothesis. If Z is greater than or equal to the cutoff, then we fail to reject the null, and the null is accepted. And we can also do the p-value method by computing the p-value off of it. Now, with mu1, the alternative, greater than mu 0. So to do this test, here our alternative is that mu is greater than mu 0, and then the null is that mu is less than or equal to the reference value. With a significance level of alpha, where the underlying standard deviation sigma is known, once again, the best test statistic is Z equals to x bar minus hypothesized value divided by sigma divided by square root of n. It's the same thing over and over and over. If Z is greater than our cutoff value, then we reject the null hypothesis in favor of the alternative. If Z is less than or equal to the alternative, then we fail to reject the null hypothesis, and the null is accepted. And once again, we can compute the p-value. Now, the power of a test. The power of a test tells us how likely it is that a significant difference will be detected based on a finite sample size n if the alternative hypothesis is true. That is, if the true mean mu differs from the mean underlying null hypothesis. So here, if I look at this fraction, x bar minus hypothesized value divided by sigma divided by square root n, this is greater than this cutoff value, multiplying both sides by sigma divided by square root n and adding the hypothesized value, we get that x bar is greater than mu naught plus that Z times sigma divided by square root n. Or we get that x bar is less than or equal to mu sub 0 Z times sigma divided by square root n. All right, and these each correspond to our hypothesis test, decisions. So now here we have an illustration of the power of a one sample test for the mean of a normal distribution with known variance. Okay, so what we're trying to do, we're trying to understand what would happen if, in fact, the true value of the expected value of the distribution is mu sub 1. All right, so I'm testing the hypothesis that mu sub 0 is equal to the true population average, but in fact, in reality, the population average is equal to mu 1. And so here we can see that in this double shaded region, if it lands in this region, this is our type 1 error. Okay, so if mu sub 0 is correct and I land here, I'm going to fail to reject the null hypothesis. But over here, if my test statistic is in this region, we reject it. And here we look at it and it flips around. So this power, this shaded region, the 1 minus beta, indicates how likely we are to make the correct decision when our hypothesized value is mu sub 0, but the true population expected value is mu sub 1. Power for the one sample t-test for the mean of a normal distribution with known variance, one-sided alternative. The power of the test for the hypothesis, null hypothesis, mu equals first value, mu sub 0, versus the alternative of mu equals mu 1. All right, so here we have two possible decisions. We're going to say either the population average is equal to this, or the population average is equal to that, and we're not accepting any other possibility, where the underlying distribution is normal and the population variance is assumed known. Then this normal function is equal to this. Now, factors affecting the power. If the significance level is made smaller, if alpha decreases, then z increases, and hence the power decreases. If the alternative mean is shifted farther away from the null mean, so they're farther apart, so the absolute value of the difference between these increases, the power increases. This is saying that these two values, if they're far apart, it's going to be easier to decide which one's the correct one to go with. If the standard deviation of the distribution of individual observations increases, then the power decreases. So if standard deviation increases, that is, the variance increases, then I have a loss in precision, the power decreases. If the sample size increases, then the power increases. Now, the power for the one sample z-test for the mean of a normal distribution two-sided alternative. The power of the two-sided test, mu is equal to mu naught versus mu does not equal mu naught. For the specific alternative, mu equals this other value that we don't know, where the underlying distribution is normal and the population variance is assumed known, is given exactly by this calculation and approximated by this. And so here we can represent graphically what is going on with the power. We can re-express the rejection region criteria in terms of x as this. So this is just a rewriting of what we had earlier. The power of the test versus the specific alternative, mu equals mu1, is given by this. So this is just hard pencil and paper calculation using 1 minus phi is equal to phi of negative x. The last two terms can be combined in this manner. And so finally, we recall the relationship here between these two, and we get this worked out for our power. And so now here's an illustration of power for a two-sided test for the mean of a normal distribution with known variance. The power of the situation is when the alternative is correct. So what is the likelihood that we would reject the null hypothesis because the alternative is the correct one? That gives us the power. Now, sample size determination, one-sided alternative. Suppose we wish to test that mu is equal to mu naught versus mu equals mu1, where the data are normally distributed with mean mu and known variance. The sample size needed to conduct a one-sided test with significance level alpha and probability of detecting a significance difference is 1 minus beta. And so if we go through and we work through the calculations, we'll actually be able to figure out, with just using some college algebra, what the n should be, because all the other values are set down and fixed, and I can get, what I want it to be. All right, so now factors affecting the sample size. The sample size increases as the variance increases. The larger the variance of the data, the larger the sample size I need to make an inference. Sample size increases as the significance level is made smaller. So if alpha is super small, then I need a lot more data to make sure that I get within the right region. The sample size increases as the required power increases. So if I want more power. So remember, alpha and beta address the likelihood of making a mistake. If I want to avoid a mistake, I can increase the sample size. The sample size decreases as the absolute value of the distance between the null and the alternative increases. So if that null 0 and or mu 0 and mu 1 are far apart, I need less data to distinguish between them. If they're close together, I need more data to detect the difference with my data. Sample size estimation when testing for the mean of a normal distribution two-sided alternative. Suppose we wish to test the null and the mean for two particular values where the data are normally distributed with mean mu and known variance sigma squared. The sample size needed to conduct a one-sided test with significant levels of alpha and 1 minus beta for the power is equal to this fraction. All right, so now sample size estimation based on confidence interval width. Suppose we wish to estimate the mean of a normal distribution with sample variance s squared and require that the two-sided confidence interval for mu be no wider than L. The number of subjects needed is approximately 4 times the z squared times s squared divided by L squared. All right, now the relationship between hypothesis test and confidence intervals for the two-sided case. Suppose we are testing either mu is equal to a particular value, or the alternative is that mu does not equal that value. It's either equal to or it's not. Then we reject with a two-sided level alpha test if and only if the two-sided confidence interval for mu does not contain the hypothesized value. So we take the confidence interval, we check to see if the hypothesized value is in that interval. If it's not in the interval, reject the null hypothesis. If it's in the interval, fail to reject. The null hypothesis is accepted with a two-sided level alpha test if and only if the two-sided confidence interval does contain the hypothesized value. The two-sided confidence interval for mu contains all values mu sub 0 such that we would accept the null using a two-sided test with that particular significance level where the hypotheses are mu equals mu naught versus mu does not equal mu naught. Conversely, the confidence interval does not contain any values mu sub 0 for which we could reject the null using a two-sided test with a significance level of the one we just established. All right, so it's a Bayesian inference. So, all right, so the probability that I'm going to get a random value from a normal distribution times sigma divided by square root n, then subtract that from x bar, and then x bar plus my z times sigma divided by square root n. So notice that x bar is the random variable. Everything else is a fixed value. The probability that probability that x bar with this stuff would be on the left of mu, and x bar with this stuff will be on the right of mu. The probability of that is equal to 1 minus alpha. To use this, we need to specify a prior distribution for mu. A prior distribution is a generalization of the concept of a prior probability, where a probability distribution of possible values for a parameter such as mu is specified before looking at the available sample data. This distribution is then modified after some sampling data are acquired to obtain a posterior distribution for mu. In the absence of data, we often have no knowledge of mu, so all possible values of mu are equally likely. This is called flat or non-informative prior distribution and is written as the probability distribution of mu is proportional to a constant. If the distribution is normal and sigma is known, then all of the information in the sample concerning mu is contained in x, and so everything that I know comes from my data, and it works out that for this problem, all the informative value of my entire data set is equal to the informative value of the sample average. All right, X bar is, so this should be X bar, is referred to as a sufficient statistic for X. To obtain the posterior distribution, we use Bayes' rule. So here I'm just using Bayes' theorem. Just rewriting Bayes' theorem basically takes probability, conditional probability, and switches the order by rescaling. However, the prior probability of mu is the same for all values of mu. Thus, the probability of mu given X bar is proportional to the probability of X bar given mu. For a continuous distribution, we approximate the probability of X bar given mu by F of X bar given mu. And so then, boom, we've got this aspect. I'm just taking the probability distribution function of X bar. And so now I'm going to take advantage of this and say that the probability that of mu given X bar is proportional to this. Now, the reason why it's proportional is because in this situation, X bar is a fixed value. This may or may not actually integrate to 1 if I integrate over all the possible values of mu. Therefore, this isn't quite a probability distribution. It's close. There is just a rescaling aspect. The distribution of mu given X bar is normally distributed with mean equal to X bar and variance equal to sigma squared divided by n, or mu given X bar is distributed normal X bar sigma squared divided by n. A posterior predictive interval for mu based on the sample data of the form of this. So I have two cutoffs. So here is mu. I'm treating it as a random variable because we're doing Bayesian statistics. Probability that's between these two fixed values is equal to 1 minus alpha, where mu1 is equal to X bar minus z sigma divided by square root n. Other cutoff, here I'm adding the same value. So we add and subtract. One sample chi-squared test for the variance of the normal distribution, two-sided alternative. We compute the test statistic here. So x squared is equal to n minus 1 times s squared divided by hypothesized variance. If our chi-squared or our x squared is strictly less than our cutoff, or our x squared is strictly greater than our cutoff, then the null hypothesis is rejected. If our x squared is between the two cutoff values, then the null hypothesis is accepted. In this region, we accept the null hypothesis. In these two, we reject the null hypothesis in favor of the alternative. All right, so p-value for a one sample chi-square test for the variance of a normal distribution two-sided alternative. All right, so now I want to do a hypothesis test on the variance of a distribution. So let's take the test statistic. Our test statistic, x squared is equal to n minus 1 times s squared divided by our hypothesized variance value. If it works out that if s squared is substantially less than the hypothesized population variance, then the p-value will be equal to 2 times the area to the left of our test statistic. If s squared is greater than the hypothesized value, then the p-value is 2 times the area to the right here. So here I'll find this value if x squared, if s squared is less than the hypothesized value for the variance, then I'm in this situation, I'm going to find this area, double it, that's my p-value. If s squared is strictly greater than the hypothesized value, then I'm in this situation, I find this using x squared, and then I double the shaded region as the p-value. And so this is just saying to, basically, we just want to use a computer to compute this for us. Don't do it manually. All right, one sample inference for the binomial distribution, normal theory methods. Okay, so it works out that if I treat my binomial random variable as the sum of one event binomial random variables, and then I divide by number of observations, then I get an estimate of the probability of success. And then boom, that's an average. I can use central limit theorem. Boom, I can approximate everything with normal distribution. So in that case, if z is less than a cutoff or z is greater than a cutoff, we reject the null hypothesis. If z is between the two cutoffs, then we fail to reject the null hypothesis. The null is accepted. Now we only want to do this when the hypothesized probability of success, the hypothesized probability of failure times n is greater than or equal to 5. Now, computation of the p-value for the one sample binomial test, normal theory method. All right, so here, this is a very simple, or not simple, a very similar situation. Basically, if I get a large enough of a sample percentage of success, then I can go with it being greater. If it's substantially lower than the hypothesized value, then I conclude that it's less. So the test statistic is observed likelihood of success minus hypothesized value of success divided by square root hypothesized probability of success times hypothesized probability of failure divided by n. This will give me a normal distribution standard normal value. Then I'm going to take this, I'm going to find where it is. I'm going to find the shaded region to the left or the right. So if it's less than 0, I go left, find the shaded region. If z is greater than 0, I find the shaded region to the right. And then for a one-sided test, that is going to be my p-value. If I'm doing a two-sided test, then I multiply by 2. All right, so computation of the p-value for the one-sided binomial test, exact method. The exact method, I have to actually go through and crunch this out. This is super easy by computer. We just drop it in the R, SPSS. It just does it like that. Easy peasy, lemon squeezy. It's no problem for us. Back in the day when people were doing it by hand, this was kind of tedious, and what they would use the central limit theorem to approximate the number we would get here using like a normal distribution. Now, if my n times hypothesized success probability times hypothesis probability of failure, if that's less than 5, then I have to use the exact calculations. All right, now the power for the one sample binomial test, two sample alternative, if our alternative is that p does not equal a hypothesized value, our null is that p is equal to a particular value, for the specified alternative, then we can compute this out, p sub 0 minus p1 absolute value, square root n over square root probability of success, probability of failure, add the z, multiply by this ratio, take the normal curve value, the sample size estimate for the one-sided binomial test, two-sided alternative. Suppose we wish to test this null of equality versus does not equal. The sample size needed to conduct a two-sided test with a significance level of alpha and 1 minus beta for the power versus a specific alternative of p equals p1 is this value here. So if I know the desired significance level, desired power, and I know the two possible values of success for the alternatives, this tells me how large of a sample size I need. I need greater than or equal to this fraction. Now, one sample inference for the Poisson distribution, one sample, the small sample test critical value method. Let X be a Poisson random variable with expected value of mu to test the hypothesis that mu is equal to mu0 versus mu does not equal mu0 using a two-sided test with significance level alpha to obtain the confidence interval based on the observed value x bar of x denoted this confidence interval. So what we'll do is to do Poisson distribution, we'll actually compute the confidence interval, and then we'll check to see where does where is our null hypothesis value? Is it outside the confidence interval or is it inside the confidence interval? If it's inside the confidence interval, we fail to reject the null hypothesis. If it is outside the confidence interval, we reject the null hypothesis in favor of the alternative. Now, one sample inference of the Poisson distribution, small sample test, p-value method. Well, then here, what we're going to do, we're actually going to compute the p-value, which means we have to do a bunch of number crunching kind of thing. This is easy peasy if I'm using R, because I can use the p Poisson function. Let mu equal the expected value of a Poisson distribution to test the hypothesis that mu does not equal mu sub 0 versus mu does equal mu sub 0. I'm going to compute yeah, so here's just how we will crunch this out. Get our p-value. And here's a p Poisson. Do the calculation for us. R makes this kind of thing really, really easy. An index frequently used to quantify risk in a study population relative to the general population is the standardized mortality ratio. It is defined as the observed divided by expected times 100 for the percent. So the observed number of deaths in the study population divided by the expected number of deaths in the study population under the assumption that the mortality rates for the study population are the same for those under the general population. For non-fatal conditions, the standardized mortality ratio is sometimes known as the standardized morbidity ratio. For this type of work, we will be using the Poisson distribution heavily. All right, so one sample inference for the Poisson distribution, large sample test. Let mu equal the expected value of a Poisson random variable to test the hypothesis that mu is equal to mu sub 0 versus the alternative that mu does not equal mu sub 0. We're going to compute the observed number of events in the study population, and then we're going to compute the test statistic. So x minus mu sub 0 squared divided by mu sub 0. And this is going to be our standardized mortality ratio divided by 100 minus 1 squared times mu sub 0. And this will be distributed as a chi-squared random variable with 1 degree of freedom under the null hypothesis. For a two-sided test at significance level alpha, the null is rejected if I get a large enough x squared greater than a cutoff, and the null is accepted if my test statistic is less than or equal to the cutoff. The exact p-value is given by the probability that chi-squared random variable with 1 degree of freedom is greater than test statistic. This test should only be used if mu sub 0 is greater than or equal to 10. An approximate confidence interval for mu is equal to this. Here we are using the Poisson distribution's variance expected value equality to work that out. All right, so now here's the acceptance region and rejection regions for one sample Poisson test. And here I set up a cutoff. I look at my data, do the computation. If my test statistic is here, I reject. If my test statistic is here, I fail to reject. The other way is I compute the value. I look at how large is the area to the right of it, and that gives me the p-value. Then I compare the p-value to the alpha level. All right, so here is that summary. In this chapter, we introduce specification of the null and the alternative hypotheses, type 1 error, type 1 error risk of alpha, type 2 error risk of beta. The power is 1 minus beta, and a hypothesis test, the p-value is the shaded region more extreme than what we observed, and there's this distinction between one-sided and two-sided tests. Methods for estimating approximate sample size as determined by the pre-specified null and alternative hypotheses, and type 1 and type 2 errors. These conditions, or these concepts, were applied to many one-sample hypotheses testing cases. Each of the hypotheses tests was shown to be conducted in one of two ways. First way is to specify critical values to determine the acceptance and rejection regions. This is a critical value method based on our type 1 error risk tolerance. The other way, second way, is to compute the p-value, then compare the p-value to our type 1 error risk tolerance. Another way is to do Bayesian inference methods. First way is with no prior information exists concerning the parameters. And another way is when substantial amount of prior information is available. And so here is a flowchart to work through. That's it. Well, that's all I've got for you. Take care and goodbye.